We're now going to look at a few examples of disubstituted benzene compounds when we involve them in the electrophilic aromatic substitution reaction. When we have multiple substituents already on the ring, predicting the product can be challenging. However, when the two groups are directed to the same position, it is fairly easy to predict the product that we're going to get. For example, if we have a methyl group para to a nitro group on benzene, since both substituents direct to the same two spots in the benzene ring, the product is very easy to predict. In the case of the methyl group, it's an ortho-para directing group, and so it would be directing a bromine to the ortho position to it, which would be these two carbons here. The para position is blocked because of the nitro group, so there's only two possible places to direct a new substituent. Nitro groups, remember, are meta-directing, and the meta position is actually the same two carbons that the methyl group wants to direct the bromine to. So the bromine, since both the methyl and the nitro group are directed to the same spot, will be located now in the product in this carbon. Because of the symmetry, it doesn't matter whether we put the bromine on the right or the left side of the molecule. When we have a disubstituted benzene compound and both groups are not directed to the same location, then generally the new substituent will go on benzene based on the strongest activator. For example, if we have a phenol in a methyl group, the phenol is the stronger activator, and so it's going to direct the new substituent, which is a nitro group, ortho to it, since the para position is blocked. So that would be directing to these two carbons. Note that the methyl group is also an ortho-para directing. The ortho positions are these two carbons, and the para position is blocked. But because the phenol is a stronger activator, it's going to predict where the nitro group will add, which would be ortho to it. And so this is the major product that we should get from this reaction. Something else to keep in mind is that a carbon on a benzene ring between two substituents is generally too hindered of a location to add any new substituents there. As an example, if we have metachlorotoluene, the methyl group, you might recall, is a weak activator, while the halogen is a weak deactivator. So the methyl group should direct the new substituent, ortho or para to it. Notice that one of the ortho position is blocked by the fact that there are two substituents surrounding it. So the halogen is very likely to add to the para position of the methyl as well as the ortho position of the methyl. Very little of this product, which has the halogen in between the two substituents, will form. And compare that to an example where we have a methyl and a nitro group ortho to each other. If we do a halogenation, because the methyl group is a stronger activator than the nitro group, it would direct the new substituent, ortho or para to it. Here's an example where we have a meta-substituted compound with bromine and a methoxy group, and we want to predict the product from electrophilic aromatic substitution of this compound. If we try to do electrophilic aromatic substitution on this meta-substituted benzene compound, the electrophile should add ortho and para to the methoxy group, which is a stronger activator than the bromine. So the electrophile should end up ortho or para to the methoxy group. Note that it's very unlikely that we're going to get a substituent in between the two groups. although that's an ortho position to the methoxy group, it is blocked by the sterics of these two substituents. In this question, we want to predict the product from the bromination of paramethylbenzoic acid. Paramethylbenzoic acid has a weak activating group in the methyl group, and it has a moderately deactivating group in the carboxylic acid. The methyl group is a stronger activator, so it should predict where the bromine adds. It should add ortho to the methyl group since the para position is blocked by the carboxylic acid. So this product here should be the major product. We want to synthesize 4-bromo-nitrotoluene from benzene. The compound we're trying to make has a bromine at the 4 position, a nitro group at the 2 position, and it has a methyl group at the 1 position. We're going to start off from benzene. So we're going to be adding 3 different substituents, and we need to think about which one we want to add first and which one we want to add last based on how these groups direct a new substituent to the benzene. In this question, we're trying to synthesize 4-bromo-2-nitrotoluene from benzene. In the process, we're going to add 3 new substituents, and so we want to think about how or what sequence we would add them in so that as we add any new substituents, they're directed to the correct position. If we try to do the alkylation first through a Friedel-Crafts alkylation, which involves methyl chloride and aluminum trichloride, we can make toluene, and then a bromination should add the bromine to either the ortho or para position, since the methyl group is an ortho-para director. That should give us a way to make para-bromotoluene, although this is not the best route to make this compound, since you might recall that because both the methyl group and the bromine are relatively small groups, I would suspect that this reaction should give you primarily the ortho substituted product rather than the para substituted product. But we'll ignore that for this synthesis. Another way to make the same compound would be to switch the order of these two substituents, how we add them. We could do the bromination first to give us bromobenzene. The bromine is an ortho-para directing group, so it should add the methyl group to either the ortho or the para position. And again, I would suspect that this reaction should give us primarily the ortho substituted product, but it does give us a way to make the para substituted product. From para-bromotoluene, we could do a nitration to add the nitro group to the correct position. Since the methyl group is a stronger activator than the bromine, it should direct the nitro group to the ortho or the para position. But because the para position is blocked, the nitro group will add to the ortho position. Notice that this compound is symmetrical, so it doesn't matter which ortho position we add them to, it should give you the same product. Another possibility that you might think about would be to add the nitro group first and then do the alkylation or bromination next. One of the problems we're going to run into is that the nitro group is a strongly deactivating group. You might recall that the Friedel-Crafts alkylation and acylation is a little finicky in that we can't do the reaction with an electron withdrawing group already existing on the ring. And so we want to save this nitro group to the end to avoid issues with the Friedel-Crafts alkylation.